Hey everyone, and welcome back to the channel. Today, we're diving into one of the most fundamental and beautiful concepts in all of physics, the classical harmonic oscillator. Now, that might sound a bit intimidating, but I promise you, the core idea is something you've seen a million times. We're going to explore it using a simple, everyday example, the mass spring system. Imagine you have a block of mass, let's say a small wooden cube, resting on a perfectly smooth, frictionless table. Now, let us attach one end of a spring to this block and the other end to a fixed wall. In its natural state, when the spring is neither stretched nor compressed, the block just sits there. We call this the equilibrium position. This is our starting point, our ground zero. But what happens when we pull the block away from the wall, stretching the spring? As soon as you let go, what does it do? It snaps back, right? And it doesn't just stop at its original position. It overshoots, compressing the spring on the other side. Then, the compressed spring pushes it back out, and it overshoots again. This back and forth motion, this oscillation, is the heart of what we're talking about today. To understand this motion, we need to talk about energy, specifically potential energy. When the block is at its equilibrium position, we define its potential energy as zero. It's just chilling. But when you stretch or compress the spring by a certain distance, let's call it x, you're doing work on the system. You are storing energy within the spring. This stored energy is what we call elastic potential energy. Here's the cool part. The amount of potential energy stored is proportional to the square of the displacement. That means if you pull the block twice as far, you store for times the energy. If you pull it 3 times as far, you store 9 times the energy. This relationship, where the potential energy is a quadratic function of the displacement, is the hallmark of a simple harmonic oscillator. Graphically, if you plot potential energy versus displacement, you get a perfect parabola, with its minimum at the equilibrium position. Now, why does the block move back towards the center? This is where the famous Hooke's law comes into play. Robert Hooke, a brilliant 17th century scientist, discovered that the force exerted by a spring is directly proportional to how much you stretch or compress it. But, and this is crucial, the force always acts in the opposite direction to the displacement. It is a restoring force because it always tries to restore the block to its equilibrium position. So, if you pull the block to the right, the spring pulls it back to the left. If you push the block to the left, compressing the spring pushes it back to the right. The further you pull, the stronger the restoring force. This constant tug-of-war is what drives the oscillation. The force is strongest at the maximum displacement points and zero right as the block passes through the equilibrium position. Let's put it all together and talk about the beautiful dance of energy conservation. When you first pull the block to its maximum distance and hold it there, all the energy in the system is potential energy. The block isn't moving, so its kinetic energy, the energy of motion, is zero. The moment you let go, the restoring force starts to pull the block back towards the center. As the block accelerates, that stored potential energy begins to transform into kinetic energy. The block picks up speed. By the time the block reaches the equilibrium position, the spring is momentarily at its natural length at this exact instant. All the potential energy has been converted into kinetic energy. The block is moving at its maximum speed, but it doesn't stop. Its inertia carries it forward, and it starts to compress the spring on the other side. As it compresses the spring, its kinetic energy starts to convert back into potential energy. The block slows down. It continues until it reaches the maximum compression point on the other side, a point exactly as far from the center as where it started. Here, for a brief moment, the block stops. All its kinetic energy is gone, and all the energy is once again stored as potential energy in the compressed spring. Then the whole process reverses. The compressed spring pushes the block back out. Potential energy turns back into kinetic energy. It zips through the equilibrium point at top speed, and so on. This continuous, seamless transfer between potential and kinetic energy is what keeps the oscillation going in an ideal, frictionless world. This would continue forever. The total energy, the sum of kinetic and potential energy, remains constant throughout the entire cycle. Finally, let's think about the classical interpretation of the system. The maximum distance the block moves from the equilibrium position is called the amplitude. If you pull the block out a little bit and let it go, it will oscillate with a small amplitude. If you give it a big initial pull, it will oscillate with a large amplitude. And how does this relate to energy? Remember, the potential energy is proportional to the square of the displacement. So, the total energy of the oscillator is determined by its amplitude. A large amplitude means you initially stretched the spring more, stored more energy, and thus the system will oscillate with a higher total energy. In classical physics, the amplitude, and therefore the energy, can be any value. You can pull it out 1 centimeter, 1.1 centimeters, or 1.11 centimeters. The energy is continuous. This simple mass spring model is incredibly powerful. It helps us understand everything from the swinging of a pendulum to the vibrations of atoms in a crystal lattice and even the oscillations of electromagnetic fields in light waves. It's a foundational concept that pops up everywhere in science and engineering. Understanding this elegant dance between force, displacement, and energy is a key step to unlocking a deeper understanding of the world around us. I hope this breakdown of the classical harmonic oscillator was helpful and gave you a new appreciation for the simple physics of a mass on a spring. It's a perfect example of how complex-sounding ideas can be understood through simple, intuitive models. You might remember the classical harmonic oscillator from your physics classes. Think of a mass on a spring, bouncing back and forth. It's a beautifully simple and predictable system. But what happens when we shrink this system down to the atomic scale? Well, things get weird, and that's where the magic of quantum mechanics begins. The classical oscillator has a potential energy that looks like a smooth parabola, a U-shape, classically. A particle can have any amount of energy. It could be oscillating just a tiny bit, or a whole lot, and everything in between. But in the quantum realm, this continuous picture breaks down. To understand how, we need to bring in the master equation of quantum mechanics, the Schrödinger equation. The Schrödinger equation is the quantum equivalent of Newton's second law. Instead of telling us the exact position and momentum of a particle, it tells us about its wave function. This wave function, often represented by the Greek letter psi, contains all the information we can possibly know about the quantum system. For the harmonic oscillator, we plug its specific potential energy, that quadratic, parabolic shape, into the Schrödinger equation. Now, solving this equation is a bit of a mathematical journey. But the result is absolutely fascinating, unlike the classical case where any energy is allowed. We find that the Schrödinger equation only has valid, physically sensible solutions for specific, discrete energy values. The solutions, our wave functions, behave like standing waves. Think of a guitar string. It can only vibrate at specific frequencies, the fundamental tone and its overtones. It can't just vibrate at any random frequency in between. The quantum harmonic oscillator behaves in a similar way. This is the concept of quantization, and it's a fundamental departure from classical physics. The allowed energy levels are not random. They follow a very specific pattern, the energy of the lowest possible state, called the ground state, is not zero. This is mind-blowing. Even at its absolute minimum energy, the quantum oscillator is still jiggling round a bit. This is called zero-point energy, a direct consequence of the Heisenberg uncertainty principle. You can't have a particle that's perfectly still at the bottom of the potential well, because then you'd know both its position and momentum with perfect certainty, which is forbidden. The energy levels are evenly spaced. If the ground state energy is E0, the next level up is E1, then E2, and so on. The gap between each level is constant. This energy spacing is determined by two key things: the classical frequency of the oscillator, which depends on the stiffness of the spring and the mass, and a fundamental constant of nature, Planck's constant, denoted by h. Planck's constant is the tiny, fundamental unit of action in the universe, and its presence is the signature of quantum effects. Each of these allowed energy levels is labeled by a quantum number, n, which can be 0, 1, 2, 3, and so on. For n equals 0, we have the ground state. For n equals 1, we have the first excited state, and so on. This quantum number indirectly tells us which energy level the system is in. The energy of any state is simply related to this number n. So what do the wave functions for these energy states actually look like? For the ground state, the n equals 0 state, the wave function is a simple bell-shaped curve, a Gaussian. The peak is at the center, which tells us that the particle is most likely to be found at the equilibrium position. But notice, the curve extends outwards. This means there's a non-zero probability of finding the particle away from the center, even in regions that would be classically forbidden, regions where the particle wouldn't have enough energy to reach. This is called quantum tunneling. Now, let's look at the first excited state, where n equals 1. The wave function looks different. It has a node, a point right in the center where the wave function is 0. This means the particle has zero probability of ever being found at the exact equilibrium position. Isn't that strange? The particle is oscillating back and forth, but it can never be found at the very center. The probability is highest on either side of the center. As we go to higher and higher energy levels, with larger n, the wave functions become more complex, with more and more nodes. The nth state will have n nodes. The particle has more energy, so it can travel further from the center, and the regions where it's most likely to be found shift outwards. Here's the really cool part. If you squint at the probability distributions for very high energy levels with a large quantum number n, you start to see something familiar. The probability becomes highest near the edges of the motion, the turning points, and lowest in the middle. This is exactly what you'd expect from a classical oscillator. A classical mass on a spring moves fastest through the center and spends most of its time slowing down and turning round at the ends of its path. This is a beautiful example of the correspondence principle. At high energies, quantum mechanics smoothly recovers the classical physics we're familiar with. So, to recap, when we apply the Schrödinger equation to the simple harmonic oscillator, the classical idea of continuous energy is replaced by discrete, quantized energy levels. These levels are evenly spaced and are governed by Planck's constant and a quantum number n. Each energy level has a unique standing wave solution, its wave function, which tells us the probability of finding the particle at different positions. From the bizarre zero-point energy and quantum tunneling in the low energy states to the recovery of classical behavior at high energies, the quantum harmonic oscillator is a perfect model system that reveals the deepest and most fascinating rules of the quantum universe. It's not just a textbook exercise. This model is crucial for understanding vibrations in molecules, the behavior of light in a cavity, and much more. Now, we're diving deep into one of the most fascinating bridges in all of physics, the connection between the strange, probabilistic world of quantum mechanics and the familiar, predictable classical world we experience every day. How can both be true? How do we get from a fuzzy cloud of probability to a solid, definite object? Stick round, because we're about to demystify the correspondence principle. So let's start with a core concept in quantum mechanics, the wave function. We often represent it with the Greek letter psi. Now, the wave function itself isn't directly observable, but its square gives us something incredibly useful, the probability density. Imagine a single electron in a box. The square of its wave function at any point tells us the probability of finding that electron right there if we were to look. Where the wave function's value is large, the probability is high. Where it's zero, we'll never find the electron. It's not that the electron is zipping round, and we just don't know where it is. Its position is fundamentally described by this wave of probability until we make a measurement. This is a huge departure from classical physics. Think about a classic pendulum swinging back and forth. If you were to take 1,000 random snapshots of it, where would you most likely find it? You'd probably catch it most often near the ends of its swing, right? The points where it momentarily stops and turns round. Why? Because it's moving slowest there. It spends the most time at these turning points. In the middle of its swing, it's zipping by at its fastest speed, so you're less likely to catch it there. The time it spends in any given region is its residence time. More time means a higher chance of being seen there. Now let's go back to our quantum particle. Say, an electron trapped in a potential well, which is like a quantum version of a valley. We can calculate its wave function and then square it to get the probability density for the lowest energy state, the ground state. Something weird happens. The probability of finding the particle is highest right in the center of the well, exactly where the classical pendulum is moving fastest and is least likely to be found. The quantum and classical pictures look completely different. It seems like they're telling us opposite stories. What gives? This is where the magic of the correspondence principle comes in, a brilliant idea championed by Niels Bohr. The principle states that for large quantum numbers, the predictions of quantum mechanics must approach the predictions of classical mechanics. What's a large quantum number? Well, quantum systems have discrete energy levels, labeled by numbers like n equals 1, n equals 2, n equals 3, and so on. The ground state is n equals 1. As we pump more and more energy into the system, the quantum number gets bigger and bigger. Let's revisit our particle in a well. We saw that at n equals 1, the probability is highest in the middle. But what happens if we look at a much higher energy state, like n equals 10 or n equals 100? As n increases, the wave function becomes much more wiggly. It develops more peaks and troughs. When we square this highly wiggly wave function, we get a probability distribution with many, many bumps. But if we kind of squint and average out those little wiggles, what do we see? The overall shape starts to change dramatically. The average probability becomes lowest in the middle and highest near the edges. Near the classical turning points, it's incredible, the quantum probability distribution starts to look exactly like the classical residence time distribution. The particle is most likely to be found where its classical counterpart would be moving the slowest. The two descriptions, which seemed so contradictory at low energies, start to merge and agree with each other perfectly in the high energy limit, our everyday world, with its massive objects and enormous energies. is essentially a world of incredibly large quantum numbers. That's why we don't see these weird quantum effects, like things being most probable where they move fastest. The underlying quantum rules are still there, but at our scale. They average out to produce the classical laws of motion that we know and trust. Let's think about this from another angle. Energy levels in a quantum system. Only certain discrete energy levels are allowed. It's like a staircase. You can be on step 1 or step 2, but not step 1.5 for a macroscopic object like a real pendulum. These energy steps are so incredibly tiny and so close together that they form a virtual continuum. The energy differences are unnoticeably small. This is another way the quantum world blends seamlessly into the classical one. The quantization of energy, a hallmark of quantum mechanics, becomes irrelevant at the macroscopic scale because the steps are too small to perceive. So, the correspondence principle isn't just a neat trick. It's a fundamental requirement for quantum mechanics to be a complete theory of the universe. It ensures that the new, more fundamental theory correctly reproduces the results of the old, established theory in the domain where the old theory is known to work. It's a reality check. If quantum mechanics didn't gracefully become classical mechanics at large scales, it would be a failed theory. But it does, and it does so beautifully. It shows us that the classical world isn't separate from the quantum world. It emerges from it. The definite, predictable reality we perceive is built upon an underlying foundation of probability and uncertainty, all governed by consistent and elegant mathematical rules. This bridge between the quantum and classical realms is a testament to the power and coherence of physics. It shows us that reality is a single, unified story, even if different chapters are written in very different languages. We just needed to learn how to translate between them. Let's dive into something super cool that's happening all around us, but mostly goes unnoticed. The secret dance of atoms in solid stuff. Imagine a solid, like a crystal of salt or a piece of metal. What does it look like at the atomic level? Well, you can picture it as a perfectly ordered, three-dimensional grid of atoms. This grid is what we call an atomic lattice. Now, these atoms aren't just sitting there motionless. They're connected to their neighbors by electromagnetic forces. For simplicity, physicists love to model these connections as tiny, invisible springs. So, you can think of a solid as a massive, intricate jungle gym of atoms connected by countless springs. This isn't just a cute analogy. It's a powerful model that helps us understand a lot about how materials behave. So, if these atoms are connected by springs, what happens when you add energy? Let's say, by heating the material up. The atoms start to jiggle and shake. They vibrate round their fixed positions in the lattice. This collective, coordinated jiggling of all the atoms is what we call lattice vibrations. This isn't random chaos. It's more like a complex, shimmering wave of motion rippling through the entire crystal. Think of it like striking a giant xylophone made of atoms. The vibrations travel through the structure. These vibrations are what we perceive as heat, the more thermal energy a solid has. The more vigorously its atoms vibrate, in the world of classical physics, the kind developed by Newton and others, we have a clear expectation for how this should work. Classical physics assumes that energy is continuous. That means an atom could vibrate with any amount of energy it wants, big or small, as long as it has some. There are no forbidden energy levels. It's like a ramp you can stand at any height. According to classical theory, the average energy of each one of these atomic oscillators, or vibrating atoms, should be directly proportional to the temperature. This is described by a concept called the equipartition theorem, which involves the Boltzmann factor. Simply put, it predicts that as you add heat, the energy is distributed equally among all the possible ways the atoms can move. And the total thermal energy just keeps increasing smoothly with temperature. This seems perfectly logical, right? If you turn up the heat, things get hotter and vibrate more. This model works beautifully for many things at room temperature and above. It successfully explains why materials expand when heated and how they conduct heat. But here's where things get really interesting. When physicists started pushing the boundaries and cooling materials down to very low temperatures, close to absolute zero, they saw something strange. The classical model began to fail, and fail spectacularly. According to the classical spring model, even at low temperatures, the atoms should still have some thermal energy and be able to vibrate, contributing to the material's heat capacity, that is, its ability to store heat. The theory predicted a constant heat capacity, no matter how cold it got. However, experiments showed something completely different. As materials got colder and colder, their heat capacity didn't stay constant. Instead, it dropped dramatically, heading towards zero as the temperature approached absolute zero. It was as if the atoms were suddenly unable to store energy in the way classical physics predicted. They were freezing out, becoming locked in place far more rigidly than the spring model allowed. This was a major crisis in physics at the end of the 19th century. The elegant, time-tested laws of classical mechanics were breaking down in the face of experimental evidence. It was clear that our understanding of energy at the atomic scale was missing a huge piece of the puzzle. The continuous energy ramp of classical physics just wasn't cutting it. It seemed that at low temperatures, the atomic vibrations weren't allowed to have just any small amount of energy. There was some new rule at play, a rule that forbade these tiny vibrations. This puzzle, the mystery of the vanishing heat capacity at low temperatures, became one of the key signposts pointing towards a revolutionary new idea. It suggested that energy, at the fundamental level, might not be continuous after all. Perhaps energy comes in discrete, bite-sized packets. This radical concept was, of course, the birth of quantum mechanics. It was Albert Einstein, in 1907, who first applied this quantum idea to the problem of lattice vibrations. He proposed that the energy of these atomic oscillators is quantized. This means an atom can't just have any amount of vibrational energy. It can only have specific, discrete amounts, like steps on a staircase instead of a continuous ramp. An atom can have 1 unit of vibrational energy, or 2 units, or 3, but nothing in between. He called these packets of vibrational energy quanta. At high temperatures, there's plenty of thermal energy to go round. The energy steps are small compared to the total thermal energy, so the staircase looks almost like a smooth ramp, and the classical model works just fine. But at very low temperatures, the situation changes. The available thermal energy becomes so small that it's not even enough to excite a single, first step of vibration. If the energy packet required to get to the first vibrational step is larger than the thermal energy available, the atom simply can't vibrate. It's stuck on the ground floor. This is why the heat capacity drops to zero. The atoms are effectively frozen in their lowest energy state because they can't absorb the tiny amounts of heat available. They need a bigger kick of energy to even get started. This quantum model perfectly explained the experimental data that had baffled classical physicists. The idea of quantized vibrations was a triumph, providing powerful evidence that the universe is, at its core, quantum mechanical. These quantized lattice vibrations are so important they were given their own name, phonons. A phonon is a quantum of vibrational energy, just like a photon is a quantum of light energy. So when you heat a solid, you can think of it as filling it up with a gas of these phonons. They are the particles of sound and heat. Understanding phonons is crucial for everything from designing better semiconductors and superconductors to understanding how heat flows through the Earth's crust. So, the next time you touch something warm or cold, remember the incredible story happening within. It's a tale of countless atoms connected by invisible springs, dancing a complex, quantum mechanical ballet. It is a story that shattered the classical view of the world and opened the door to the strange and wonderful reality of quantum physics, all hidden within the simple act of a solid being hot or cold. It's a beautiful reminder that even in the most ordinary objects, there are extraordinary secrets waiting to be discovered. We're diving deep into a concept that completely changed how we understand solids, Einstein's model of heat copper. City. You might remember from classical physics that the heat capacity of a solid should be constant, regardless of temperature. But experiments showed something completely different. As temperatures approach absolute zero, the heat capacity of solids mysteriously vanishes. It just drops to 0.y. Classical physics had no answer. This puzzle, known as the Coulomb-Pettit anomaly, was a major headache for scientists at the turn of the 20th century. The hero who stepped in to solve this mystery was none other than Albert Einstein in 1907. He proposed a radical idea. What if the energy of the atoms vibrating in a solid wasn't continuous, but quantized? This was a groundbreaking thought, inspired by Max Planck's earlier work on black-body radiation. Planck had suggested that light energy comes in discrete packets, or quanta. Einstein took this idea and applied it to the mechanical vibrations of atoms in a crystal lattice. Let's visualize this. Imagine a solid as a huge, orderly grid of atoms, all connected by springs. In the classical view, these atoms can vibrate with any amount of energy. They can jiggle a little, or a lot, or anywhere in between. But Einstein said, no, that's not right. He proposed that the atoms can only have specific, discrete amounts of vibrational energy. Think of it like a staircase instead of a ramp. You can stand on the first step, or the second step, but you can't hover in between. The energy levels are quantized, described by the formula E equals n times h times nu, where n is an integer. Each is Planck's constant, and nu is the vibrational frequency of the atom. This single assumption changes everything. In classical statistics, to find the average energy, we would integrate over all possible continuous energy values. But now, with quantized energy levels, we can't use an integral anymore. We have to replace it with a discrete sum. We sum up the possible energy states, weighted by their probability according to the Boltzmann distribution. This might sound like a minor mathematical detail, but it has profound physical consequences. So, how does this explain the vanishing heat capacity? At very high temperatures, the thermal energy available is huge compared to the spacing between the quantized energy levels. The steps on our energy staircase are so tiny that it basically looks like a continuous ramp again. In this regime, the quantum model gives the same result as the classical Coulomb-Pettit law: the heat capacity is constant. This is great because it matches experimental observations at high temperatures. But at very low temperatures, things get interesting. The available thermal energy, which is proportional to the temperature, becomes very small. It becomes so small that it is less than the energy required to excite an atom from its ground state to even the first vibrational level. Remember, the atoms can't just absorb a tiny bit of energy. They need to absorb a whole quantum, a full step up the ladder. If the temperature is too low, Most atoms simply don't have enough energy to make that jump. They get frozen in their lowest energy state, the ground state. Because most atoms are stuck in the ground state and can't absorb thermal energy, they can't contribute to the heat capacity. As the temperature approaches absolute zero, almost no atoms can be excited. Consequently, the solid's ability to store heat energy plummets, and the heat capacity drops to zero. This is exactly what experiments had shown. Einstein's model, based on the simple idea of energy quantization, beautifully explained this long-standing puzzle. To make this more concrete, Einstein's model gives us a specific formula for heat capacity as a function of temperature. This formula involves a special temperature, now known as the Einstein temperature, which is characteristic of each material. This temperature, theta E, is related to the vibrational frequency of the atoms in the solid. It's defined as Planck's constant times the frequency, divided by the Boltzmann constant. A material with stiff atomic bonds, like diamond, will have a high vibrational frequency and thus a high Einstein temperature. A material with softer bonds, like lead, will have a lower frequency and a lower Einstein temperature. The model predicts that if you plot the heat capacity against temperature, all materials should follow the same universal curve. Once you scale the temperature by their respective Einstein temperature, and when scientists went to the lab to check, they found remarkable agreement. Experiments confirmed that the heat capacity of various solids did indeed drop off at low temperatures, following the general shape predicted by Einstein's formula. By fitting the experimental data to the model, physicists could even determine the value of the Einstein temperature for different materials, giving them insight into the vibrational properties of the atoms within. Of course, the model wasn't perfect. It made a simplifying assumption that all atoms in the solid vibrate independently and with the same single frequency. In reality, the atoms vibrate collectively in complex modes with a whole spectrum of different frequencies. A later, more refined model by Peter Debye in 1912 took these collective vibrations, or phonons, into account and provided an even better fit to the experimental data, especially at the lowest temperatures. However, we can't overstate the importance of Einstein's work. It was the first time that the concept of energy quantization was successfully applied to explain the properties of matter, beyond Planck's work on radiation. It provided powerful, tangible evidence that the quantum world wasn't just a strange theoretical idea. It had real, measurable consequences in everyday materials. It showed that quantum mechanics was essential for understanding the properties of solids. So, to recap, the mystery of the vanishing heat capacity was solved by Einstein's brilliant insight. He proposed that atomic vibrations in a solid are quantized. This means atoms can only absorb energy in discrete packets, at low temperatures. There isn't enough thermal energy to excite the atoms to higher vibrational states. So they can't store heat, and the heat capacity drops to zero. This simple yet profound idea not only solved a major physics puzzle, but also solidified the foundation of quantum theory, paving the way for our entire modern understanding of materials science. It is a perfect example of how a simple quantum idea can have a massive impact on our understanding of the macroscopic world. Now, you've probably heard about the early triumphs of quantum theory. At the turn of the 20th century, physicists were stumped by things like black body radiation. Classical physics predicted that a hot object should emit infinite energy, which obviously doesn't happen. Max Planck came along and proposed a radical idea. What if energy isn't continuous, but comes in discrete packets, or quanta? This single idea beautifully solved the black body problem and, along with Einstein's explanation of the photoelectric effect, kicked off the quantum revolution. It felt like we had found a new, Fundamental rule of the universe, quantization, was the key. But as is often the case in science, the deeper you look, the stranger things get. This simple idea of just chopping up energy into little bits works wonders for some problems, but it falls apart when we try to apply it to more complex systems. It's like learning the alphabet helps you read simple words, but it doesn't prepare you for the intricate grammar and poetry of a full novel. For instance, how do these quantized particles interact with each other? What governs their motion and behavior over time? Just saying energy is in packets isn't enough to build a complete picture of an atom, let alone a molecule or a star. The early quantum model was a fantastic start, but it was just the prologue to a much more bizarre and mind-bending story. Scientists realized they needed a completely new framework, a new language to describe this hidden reality. That new language is built around one of the most important and strangest concepts in all of physics, the wave function. So, what is it? Imagine you want to describe a particle. Like an electron. In classical physics, you just say, it's right here. And it's moving this fast. Simple, but in the quantum world, it's not so clear-cut. The wave function, developed by Schrödinger, doesn't tell you where the particle asterisk is asterisk instead. It gives you the probability of finding the particle at any given point in space if you were to look for it before you look. The particle isn't in one single place. This is where it gets really wild. The particle exists in a state of superposition, which means it's effectively in all possible places at once. It's a smear of potential, a wave of probability. Think of it like a spinning coin. While it's in the air, it's not heads or tails. It's a dynamic combination of both possibilities, only when it lands when we make a measurement does it choose a state. This concept of superposition is at the very heart of quantum mechanics, and it's what makes the quantum world so fundamentally different from our everyday experience. This leads to a really profound and perplexing question. Where does the quantum world and our familiar, classical world begin? If atoms and particles are governed by these weird rules of superposition and probability, why don't we see everyday objects doing the same thing? Why isn't your chair in a superposition of being in the living room and the kitchen at the same time? This is known as the quantum classical boundary problem. We are made of atoms, and atoms obey quantum mechanics. So why don't we? There are a few ideas. One popular explanation is a process called decoherence. It suggests that as a quantum system interacts with its environment bumping into air molecules, absorbing photons, and so on, its quantumness leaks away very quickly for a large object like a chair, which is constantly interacting with trillions upon trillions of particles. This happens almost instantaneously. Its superposition collapses so fast that we only ever see it in one definite state. But this is still an active area of research. We don't have a definitive answer for why the solid, predictable world we see emerges from the hazy, probabilistic quantum realm that underlies it. The boundary is fuzzy. And it's one of the biggest mysteries in physics. And that brings us to the ultimate puzzle, the elephant in the room of quantum physics, the measurement problem. This is best illustrated by one of the most famous thought experiments ever conceived, Schrödinger's cat. Imagine you place a cat in a sealed box. Inside the box with the cat is a tiny amount of radioactive material. The atom is in a superposition it both has and has not decayed. If the atom decays, it triggers a detector, which releases a poison. And the cat, well, if it doesn't decay, the cat is fine. According to the laws of quantum mechanics, until we open the box and make a measurement, the entire system is in a superposition. The atom has both decayed and not decayed. The poison has been both released and not released, and the cat is simultaneously alive and dead. This is obviously absurd in our everyday world. A cat can't be both. But the math of quantum mechanics insists that it is. The big question is, what constitutes a measurement? What is it about the act of observing that forces the universe to pick one reality out of the many possibilities? Does it require a conscious observer? Does the cat itself count as an observer? Or is it decoherence, as we just discussed? Nobody knows for sure. The measurement problem shows that, despite its incredible success in predicting experimental results, quantum mechanics is still incomplete. It gives us the probabilities, but it doesn't tell us the story of how one of those probabilities becomes our reality. It is a profound mystery that suggests there is still a huge piece of the puzzle about the nature of reality itself that we have yet to find. So, from the simple, neat idea of energy packets to the mind-bending paradoxes of superposition and Schrödinger's cat, quantum mechanics is a journey that gets stranger the further you go. It challenges our most basic intuitions about reality, existence, and our own role as observers in the universe. What do you think is happening when a measurement is made? Let me know your favorite interpretation in the comments below. Thanks so much for watching, and if you enjoyed this journey into the unknown, be sure to like and subscribe for more. See you next time.